In this video, we're going to begin looking at integration to find volumes of revolution and volumes with known cross sections. And because this is a video in BC, I'm assuming that you have seen these things before and have a general understanding of them. If not, you may need to look back at some AB videos where this is just being introduced. And in the interest of time, in all of these, I am going to set up the integral and rely on the fact that you could either do the integral by hand or use your calculator to find the actual volume or area. Okay? So first, it says find the area bounded by the function and the x-axis. So this is simply the integral from 0 to 4 of the function. Okay? And that will give us the area under the curve. Now this is one that easily we could do by hand. The antiderivative, of course, would be 2x minus 1/3 x cubed. Plug in 4, plug in 0. Easy enough to do by hand. Next, if this thing were rotated around the x-axis. So I'm going to pick a spot here, just like this, and I'm going to say it was rotated around the axis. Okay. So, like this. The reason I'm doing that is I want to talk about the formula briefly again. What we're trying to do here is to add up an infinite amount of cylinders where the height of the cylinder is getting smaller and smaller. Similar to when we would first find area and we would look at rectangles and the width of the rectangle would get smaller and smaller. So imagine this little almost rectangular slice being rotated around. Now if you looked at this thing head on, you would see a circular shape. So the area would be pi r squared, and the height of my cylinder we would call dx. And again, this is something that I'm kind of relying on the fact that you saw last year, and I'm going through it pretty quickly, but if you need more help, you might want to go back and look. So a cylinder, I'm just going to write cylinder, would have a volume of pi r squared h. Well, for us, that's going to be pi. The radius is simply the value of the function, so f of x. And the height, this piece right here, we call dx. So I would integrate from 0 to 4. I like to pull a constant multiplier out front. So pi, f of x was 4x minus x squared dx. Oh, excuse me, it was pi r squared. So right back here I should be putting a squared on these things. Like that. Okay? So let's just do again, pi r squared h. And if you had to integrate this by hand, you would actually square this out. You know, write 4x minus x squared times 4x minus x squared, multiply it out, and find the antiderivative. Okay? Now, if instead of rotating around the line y equals, or around the axis, I was rotating around the line y equals -2. So imagine this line down here. So now I'm rotating, and it would look, of course, much bigger, something like that. The radius now would be the function's value plus 2 more. So my cylinder would have pi, and the radius would now be the function's value plus 2h. Okay? And really wrap your head around that pi, to get the radius, of course the function only tells me how far off the axis I am, but if I'm rotating around -2, then the radius just got 2 units bigger. So writing this now in our notation, we'd have pi, 0 to 4. The radius should be 4x minus x squared plus 2 dx. Like that. Okay. Now, if I had to rotate around something above it, like y equals 6, this. Now I'm taking the shape and I'm rotating it up. Well, now there would be kind of a hollowed out part in the middle. Okay, if you want to think about that, you're rotating the entire shape up, but there's kind of this hollowed out part in the middle, kind of like a washer or a donut. So the important thing to notice here is that there are two radius. One of them is simply the 6 minus the function. That's one radius. The other radius is simply 6. It's just all the way down right here to the axis. Okay, we have two radius. Now, when you are rotating this thing around, you end up with a shape that kind of looks like head on, that would look like this. Okay, and we would of course do pi times the big radius squared minus pi times the little radius squared to find the total area that's kind of shaded in there. And that's what we're going to do again, is we're going to simply integrate these two things. Now, you'll notice I could factor a pi out, right? And that's what I'm going to do. I'm going to factor a pi out and just have r squared minus r squared. Okay, so the big radius is just 6. Okay, and by big radius I just mean the outer part of the circle is always going to be 6. The inner part of the circle is 6 minus the function's value, because the function tells us how far off the axis we are. So this is 6 minus the function. Like that. Now again, I'm going through this pretty quickly. I'm relying on the fact that you have seen it before, but I want to point out that really all we're doing here in every case is finding the area of the face, kind of what we're looking at. So in this case right here, pi r squared, that's the area of a circle, and we let this serve as the height. Okay, so just notice that we've got pi r squared here. Here, again, we had pi r squared. It just, let me include the squared, it just so happened, of course, the radius was 2 units bigger. Here, we're finding the area of that donut, big circle minus the little circle. So all we're ever doing is really finding the area of the face and letting the dx serve as the height. Okay, let me do a couple more. So now, cross sections perpendicular to the x-axis. And again, you've seen this before, but let's just think about what that would look like. That means that they're perpendicular to the axis, and we are building up off of the shape. We're building little squares, okay? Something like that. Now, I just want you to think about, of course, I usually draw a square, and I think, well, area of a square is, of course, just the base squared. Now, volume of this little disk is base squared times its height, but much like the previous example, height is just going to be the dx. So you need to say, well, how do I get the base? Well, the base is simply the value of the function. So the area would be the value of the function squared, because this is your base. So to find the total volume, we simply integrate that area like that. Now, if instead of squares, it were semicircles. Okay, I'm going to draw some semicircles in here. I know it's getting a little crowded. So semicircles like this. Let's just think about a semicircle. Okay, so we got a semicircle. Now the area of a semicircle, of that face, is 1/2 pi r squared. Of course, the volume would be that area multiplied by dx. So let's now think about the radius in terms of the function. Okay. So right up here you can see that the value of the function is not the radius, instead it is the diameter. So we have to take the value of our function and divide it by 2. Now this throws people sometimes because they see that we're dividing by 2 twice. Let me just remind you what both things mean. The 1/2 pi means, the 1/2 here means we're only finding the area of half the circle. The 2 down here means that the function provides the diameter, so dividing by 2 we get the radius. And again, to find the total volume, we simply integrate our area. That's it.